Good morning, student. Today we are going to start Physics chapter 8 under unit 3, torque on a current carrying loop. So first of all, what is torque? Actually, torque is that whenever a object is in motion, that time what type of force is required, that is called torque. Here you can see torque on a current loop in a uniform magnetic field. So first, what is uniform magnetic field? The field which is originated by magnet, which is called magnetic field, and the magnetic field having the same magnitude as well as the direction is the same, at which region, that is called uniform magnetic field. Now, a current loop, a current carrying loop or a wire which carries current, which is situated under the uniform magnetic field, then what type of torque is produced inside the current loop in a uniform magnetic field, that is only we will see here. So see, this is a current carrying loop, name is that PQRS, and this is the this is B by B magnetic field. It is called uniform magnetic field. Now we can see here this current loop placed in this uniform magnetic field which is experience the torque. Now the wire name is PQRS, which carries current I. We can see here from S to P, P to Q, Q to R, R to S. Okay. Now it is placed inside this magnetic field. Now we can see PQ and RS, which having the side L, rectangular, that is meaning length and breadth both they have. So both the two sides are L, these two sides are breadth. Now we know that if a rectangular coil force in the magnetic field which is produced a force, this force value is I into L cross B. Okay. If force is I into L cross B, so we can see ILB sin theta, cross product sin theta, and theta is here 90 degree, so sin 90 is equal to 1, so we can easily write ILB. So F1 and F2 for both the two sides, F1 equal to F2 is equal to ILB. Now we will see the force F1 is in this direction, F2 is in that direction. See, this is F1, it is placed like that, upward direction. This is F2, so it is placed like that, F2 direction. This is the down direction. Okay. Now we can see F1 and F2, this is having a distance between them, and we can see this is the 90 degree angle it can produce here, and we see this is the axis of loop. N prime is the axis of loop. Understood? Now see that this is small b. From where this small b? This is the breadth. QR is equal to breadth. So if you placed F1 upward direction, so you can see this is that direction. So that's why we can write here this is the B. Okay. Now you see, if we consider theta is the angle, so here this B is having both the two components. One component is B sin theta, one more component is B cos theta. But we need only the perpendicular distance, because we know torque is equal to force into perpendicular distance between the two forces. So B sin theta is the torque is equal to force into perpendicular distance. We can see here. And as we know, the perpendicular distance is the B sin theta, perpendicular distance between the two forces F1 and F2. This is B sin theta. So we can write here force into perpendicular distances b sine theta, and force value came ILB. So here we can write ILB into b sine theta. As we know, length into breadth is equal to area of rectangle. So any rectangular shape is having this area, length into breadth. So we can write here I as it is, B as it is, sine theta as it is, and L cross B A. So we can write the magnitude of torque is IAB sine theta. So for this it came torque value, torque on the current loop whenever the current loop is placed in the uniform magnetic field, IAB sine theta. And through this we can see this F3 and F4, they are both the two forces acting along in the same line of action. That's why this F3 and F4, they are cancelling each other. So total torque on this loop is IAB sine theta, which is acts on it. And now it is torque in the vector form. M is equal to NIA. So the unit is that ampere into meter square. So we can write torque as the form of the magnetic moment, that is M into B, NIA, M into B into sine theta. So torque is equal to M cross B, M vector magnetic moment cross magnetic field.